So let's start with heteroskedasticity. What I've done here is reproduced the 6 assumptions for linear regression, and by now you should know these assumptions quite well. One of the assumptions is that the variance of the error term is the same for all observations, and this situation is called homoskedasticity. We see a graphical representation here. So notice that the variance of the error terms is roughly the same along this regression line. But what if this assumption is violated? An example is shown over here. Notice that the variance of the error term is relatively low over here, but in this region, the variance of the error term has increased. So clearly, assumption 4 is violated, and this situation where the variance of the error term is not the same is called heteroskedasticity. With heteroskedasticity, we have 2 major types or categories. One is unconditional and the other is conditional. With conditional heteroskedasticity, there is a relationship between the variance of the error term and the independent variable. So if you look at this diagram, as x increases, and x is our independent variable, the variance of the error term goes up. So we can say that the variance of the error term is conditional on x, and this is a problem. The issues that we'll talk about later have to do with conditional heteroskedasticity. The other type of heteroskedasticity, which is not a problem, is unconditional heteroskedasticity. Here the variance is not constant, but the variance does not depend on the independent variables. So in general, when we talk about issues and consequences, we are talking about conditional heteroskedasticity. So now, what is the impact or what are the consequences of conditional heteroskedasticity? One consequence is that the f-test for the overall significance of the regression is unreliable. So we might get a relatively high test statistic, but that test statistic is not reliable. The next point is that the coefficient estimates are fine, but the standard error is understated. So what this means is, when we run a regression, we'll obviously get values or estimates for the regression coefficients. Let's say we have B0 is equal to 0.6 and B1 is equal to 1.2. So these are the coefficient estimates. We are saying that these will be okay, but the standard error is understated. If the standard error is understated, the t-stat will be inflated. Remember, we calculate the t-stat by taking the estimate. So if we are calculating the t-stat over here, it will be 1.2 minus the hypothesized value. Let's say the hypothesized value is 1, and then we divide by the standard error. If the standard error is understated, then the t-stat will be overstated. And if this happens, then we might incorrectly reject the null hypothesis. So we might have a situation where the critical value is 2 and the actual t-stat should be 1.8. But because of the lower standard error, the inflated t-stat might be 2.8. And if we use this 2.8 and compare it with the critical value, we might reject the null hypothesis, and we might actually incorrectly conclude that there is a significant relationship, even though a significant relationship does not exist. This is called a type 1 error. So you need to remember these consequences of conditional heteroskedasticity. Now the question is, how do we test for heteroskedasticity? One approach is to look at the scatter plot, and if we clearly see a change in the variance of the error term, which depends on the x variable, then we have heteroskedasticity. But when we have regression with multiple independent variables, it might not always be easy to interpret a scatter plot. So we use the Bruch-Pagan test, and you need to remember this. To test for heteroskedasticity, we use the Bruch-Pagan test or the BP test. The null hypothesis here is that there is no heteroskedasticity. So the alternate hypothesis is that we do have heteroskedasticity. With the Bruch-Pagan test, we regress residuals with x. So we take each of these residuals and the residual amount is regressed against the x variable. The Bruce-Pagan test statistic then is the R squared that we get from this regression, and that R squared is multiplied by N, which is the number of observations. So this gives us a BP test statistic. The BP test statistic is compared with a critical value. That critical value is obtained from the chi-squared table. If the Bruce-Pagan test statistic is greater than the critical value, then we reject the null hypothesis. And remember, here the null hypothesis is that we do not have heteroskedasticity. So if the null hypothesis is rejected, that implies that we do have a heteroskedasticity problem. And I hope that also makes sense over here. If R squared is large for this particular regression, where we are regressing residuals with X, that means that there is a meaningful relationship between the X variable and the error term or the residual. And obviously, if that is the case, then we do have a heteroskedasticity problem. With respect to correcting for heteroskedasticity, there are two major approaches: robust standard errors and generalized least squares. With robust standard errors, the regression software corrects the standard errors of the linear regression model's estimated coefficients to account for conditional heteroskedasticity. Now, you might recall that with a regression output, we have values for the coefficients. So we might have B0, B1. What is reported first is a value for the coefficient. So for example, with B1, we might have a value of 1.3. Then the standard error is reported. So there will be some standard error term, and then the t-stat. The t-stat is equal to the estimated value here minus the hypothesized value divided by the standard error. When we tell the regression software to use robust standard errors, what the software will do is adjust the standard error term. And as we said before, with conditional heteroskedasticity, the standard error is understated. So this correction will cause the standard error to go up. If the standard error is increased, this is the more robust standard error, then the value of the t-stat will come down. And that will be the appropriate value of the t-stat, which should be used when we do hypothesis testing related to B1. The second possible approach is generalized least squares. Here we modify the original regression equation in an attempt to eliminate heteroskedasticity. Moving on to another possible violation, which is serial correlation. Here again, I have reproduced the linear regression assumptions, and assumption 5 is that the error term is uncorrelated across observations. But what if we have a situation like this? Here is our independent variable, this is the dependent variable, this is our scatter plot or our various observations. If we draw a regression line, we have something like this. Now here, notice that we do have a serial correlation issue, which means that the errors are correlated across observations. The error term here is positive, then it's again positive, then it's again positive. So we have what's called positive serial correlation, because when we see this positive error term, we can predict that the next error term is also going to be positive. Over here we have negative error terms, and when we see these negative error terms, we can predict that the next error term will also be negative. And this sort of a situation is called positive serial correlation. And where each error term is correlated with the previous error term, then this is called first order positive serial correlation. Another term for serial correlation is autocorrelation. Error terms are correlated across observations. The problem of serial correlation often happens when we are evaluating time series data, especially when there is a seasonality effect. This is something we'll see in more detail in the next reading. But for now, you need to understand that one of the assumptions of linear regression is that the error term is uncorrelated across observations. And when this assumption is violated, we say that we have a serial correlation problem. Now, what are the consequences of positive serial correlation? The curriculum focuses on positive serial correlation, so that's what I've also done. I'll briefly allude to negative serial correlation on the next slide. So if we do have positive serial correlation, then the F statistic may be inflated. The coefficient estimates are fine, but the standard error is understated. So this is similar to what we saw earlier with heteroskedasticity. With our regression equation, we'll have B0, B1, B2, etc. So the coefficients themselves are fine, but the error term is understated, which means that the t-stat will be inflated. So the statistical inference that we do with respect to these coefficients will be compromised. What might end up happening is that with an inflated t-stat, we might incorrectly reject the null hypothesis and make a type 1 error. This is the same issue that we had with heteroskedasticity. In other words, we might incorrectly assume that there is significance, even though in reality there is no significance. Now, how do we test for serial correlation? As before, one approach is to simply look at the scatter plot, but that might not always be easy if we have multiple independent variables. So what we should do is look at the Durbin-Watson statistic. The regression software will generate the DW statistic. Here is the formula for the DW stat, but this is rather complicated, and in an exam world, you are not expected to actually make calculations based on this formula. The more important formula for you is this. The DW stat is equal to 2 times 1 minus the correlation. For this formula, we have to use very large samples. So given large samples, the DW stat is approximately equal to 2 into 1 minus R. R is the sample correlation between the regression residuals from one period and those from the previous period. So notice with this formula, if we have the DW stat, then the sample correlation or R can be estimated. So let's look at a very simple example. Let's say that our regression software reports a DW stat of 0.4. Then using this formula, we can say that 0.4 is approximately equal to 2 into 1 minus R, which means that 1 minus R is approximately equal to 0.2. So R is approximately equal to 0.8. So notice with the DW given, we can estimate the value of R. Now here is another important picture. So notice from this formula, if R is 0, in other words, there is no correlation, then the DW stat will be 2 into 1 minus 0, which is 2. So a DW of 2 means that we have no serial correlation or R is 0. On the other hand, if DW is 0, then what is R? So if we plug in 0 over here, then R is going to be 1. A value of 1 for R means the DW is 0. And this would mean that we have very positive serial correlation. So DW stat that is very low, which means close to 0, would imply positive serial correlation. And a DW stat that is closer to 4 would mean that we have negative serial correlation. So notice if we have 4 over here, then R will be minus 1. Now let's look at the formal test. When we do a DW test, there is a critical value, but that critical value lies in a range between DL and DU. So let's say we are focusing on positive serial correlation. So we are in this region. There will be a DL and a DU. So there is some lower limit and some upper limit. If we have a DW stat that is less than DL, then we reject the null hypothesis that there is no positive serial correlation. In other words, we believe that there is positive serial correlation. If the DW stat is greater than DU, so let's say this is DU, if our DW stat is over here, then we fail to reject the null hypothesis that there is no positive serial correlation. And if our DW stat is in this region, then our test is inconclusive. So let's look at the simple example. Say the dw stat is 0.3. So our dw is over here at 0.3. And let's say that dl is 1.65. So dl is over here 1.65. In this case, our dw stat is clearly lower than dl. Therefore, we can reject the null hypothesis that there is no positive serial correlation. In other words, we believe that there is some positive serial correlation. Now, as I said before, the curriculum doesn't really talk much about negative serial correlation, but you can see here that if we have a high dw value, which is close to 4, then clearly we have negative serial correlation. And here again, there will be a range. So if the dw stat is in this range, then we can conclude that there is negative serial correlation. If the dw stat is in this range, then the evidence is inconclusive. And if the dw stat is over here, then that would imply that there is no serial correlation. So for us, an ideal scenario is that the dw is 2, which would imply no serial correlation. Now, how do we correct for serial correlation? Here again, there are two approaches. One is the Hansen method, and the other is to modify the regression equation itself to eliminate serial correlation. With respect to the Hansen method, we adjust the coefficient standard errors for the linear regression parameter estimates to account for serial correlation. This is similar to what we saw earlier with robust standard errors. So we correct the standard errors, and correcting the standard errors means that we effectively correct the t-stat. So that's the Hansen method. Moving now to multicollinearity. One of the assumptions of linear regression is that the independent variables are not random, and there is no exact linear relation between two or more of the independent variables. Multicollinearity is a violation of this assumption. So with multicollinearity, two or more independent variables or combinations of independent variables are highly but not perfectly correlated with each other. So remember this definition of multicollinearity. The consequences of multicollinearity are that estimates of regression coefficients are imprecise and unreliable. Now contrast this with what we've seen earlier. With both heteroskedasticity and serial correlation, the estimates of the regression coefficients are fine, but the standard error is understated. Here, even the estimates of the coefficients are imprecise and unreliable, and the standard error is inflated. So earlier with heteroskedasticity and serial correlation, the standard error was understated, which meant that the t-stat was overstated. But here with multicollinearity, the standard error is overstated, which means that the t-statistics are understated. How do we detect multicollinearity? With multicollinearity, we need to recognize that it is often a matter of degree rather than absence or presence. In other words, there will generally be some multicollinearity. We are concerned with the amount of multicollinearity. Obviously, if the multicollinearity is very low, then that's okay. But if we believe that there is a relationship or a significant relationship between two or more independent variables, then we do have a problem. What are the symptoms? How exactly do we detect this problem? The most important symptom is that with a regression, we have a high R squared and a significant F stat. So the overall regression appears to be significant, but the T stats are very low. So if we see both of these, where on the one hand, the R squared and the F stat are high, but the T stats for the coefficients are very low, then this implies that we might have multicollinearity. We might also look at the pairwise correlation, but this only works if we have exactly two independent variables. But generally, this is not the case. We might have one independent variable or more than two independent variables. So the better approach is to look at the R squared and the F stat as well as the T stats for the coefficients. How do we correct for multicollinearity? The most direct approach is to exclude one or more of the regression variables. Another approach is to experiment with including or excluding different independent variables. Now, what I want you to do is go over example 9 in the curriculum, and if you want, you can watch my example video related to this particular example.